Okay, everyone, have been given the go, so let me start. So this is a session sponsored by the NCAR. There is our banner. That is the National Center for Econometric Research. This is an organization, a consortium of several institutions, including, of course, QUT, where you are, and UQ, where I work. And we're most pleased to be sponsoring this session. The speaker today is Professor Federico Bandi, and he's Professor of Economics and Finance. He's also the chair of the Finance and Economics Committee at Johns Hopkins University Carey Business School. He's the co-editor of the Journal of Financial Econometrics and currently associate editor of 3 journals, Econometric Theory, Journal of Business and Economics Statistics, and Econometrics Journal. Federico's research is in the area of financial econometrics, as most of you would know, continuous time asset pricing, and empirical market microstructure. And he's not only a top researcher, but also has won teaching awards, so that should make for a very good lecture. And so we're looking forward to his presentation, which is entitled Low-Frequency Asset Pricing Dynamics. And it will be about an hour, and then after that we might have a chance to ask questions if Federico finishes with enough time, right? Okay, so let me get your slides. And,
Does it work? Can you hear me? Does it work now? Can you hear me now? Yeah, you can? Okay, perfect. All right, so I'm absolutely delighted to be here. Thank you for being here with me. So what I'd like to talk about today is work that I've done over the last few years. This is work on low-frequency asset pricing. There are a number of people are involved in this project. The names of those people are going to appear on the slides very soon. Well, let me get to it. I have quite a bit to cover, and I know that I don't have too much time. So here is a premise. We all estimate economic relations, and what we typically find is that when we estimate economic relations, no matter what they are, think about stock return predictability relations, think about Fisher effects, think about risk-return trade-offs. Whatever you have in mind, what you typically find is that they look very different in terms of estimates if you change the frequency of observation. In other words, economic relations may look very different at different horizons. Now, this is fairly well accepted, and in fact, what I'm going to do is I'm going to quote from the 2013 Nobel Committee. So this is the quote. There is no way to predict whether the price of stocks and bonds will go up or down over the next few days or weeks, but it is quite possible to foresee the broad course of prices of these assets over longer time periods, such as the next 3 to 5 years. So what that means is that if you think about predictability relations, there's really not a lot in relatively high frequency data, or if you want, over relatively short time horizons, say a day or a month. But predictability seems to be in the data as you go to longer horizons. So again, economic relations look very different at different horizons. Now, the way in which we think about different horizons when we deal with economic data is typically the following. We start with a high-frequency model, and we aggregate. That's what we all do. That's what the profession has been doing for a number of years. So since we do that, in effect, there's two aspects to this problem. One aspect is all relevant economic information is contained into high-frequency shocks, and the low-frequency shocks are simply aggregates of the high-frequency shocks. That's number one. Number two, if we go back to predictability, which is the substantive core of the Nobel Committee statement, mild short-term predictability over a relatively short time horizon and strong long-run predictability are really two aspects of the same coin. Why? Because it's one model. We start with a very, well, it may not be a very high-frequency model, but we start with a high-frequency model and then we aggregate it. So again, the two aspects, mild short-term predictability and strong long-run predictability, have to be the flip sides of the same coin. They have to be delivered by the same model. John Cochrane says they are reflections of a single underlying phenomenon. What he calls a phenomenon is nothing but the underlying model. So let me show you what I mean in the context of a very simple example. This is the most classical predictability model in the literature, and I guess it's sort of the founding block of much of the work on predictability. YT plus 1 is excess returns. Excess returns, for example, on the market. XT is a predictor. The predictor has a law of motion. The law of motion of the predictor is very simple. The law of motion of the predictor is simply an autoregressive process of order 1. Rho captures persistence, as we all know. Typically, for most of the predictors we deal with in practice, rho is very, very close to 1. So think about a predictor like the dividend yield. Think about earnings to price. Think about book to market. So any financial ratio would have a rho which is fairly close to 1. This is important, and it's important to sort of interpret the outcome of this type of model. So let me just focus on the most disaggregated model that people write, which is the model up there. What you find is that if the shocks to you are fairly large, it's very, very hard to detect any sort of predictability, even if predictability is, in some sense, in the data. And this is a typical signal-to-noise type problem. The noise is too large for beta to be estimated with any accuracy. So lack of short-term predictability may just be the result of a signal-to-noise type problem. But now let's start aggregating. So let's go to lower frequencies. Now, aggregating a model like that is relatively simple, right? So let me go to a two-period aggregation. YT plus 1 plus YT plus 2. So now I'm predicting returns over 2 periods rather than over 1 period. Now, the model tells me exactly how to do that. Alpha plus beta xt plus ut plus 1, and of course, alpha plus beta xt plus 1 plus ut plus 2. Now, let me collect x. I can do that easily. Now, of course, I know what the law of motion of xt plus 1 is because it's given by the model again. So what I find when I aggregate over 2 periods is that the true slope now becomes beta times 1 plus rho. Now, if rho is very close to 1, and of course, rho is very close to 1 for a lot of the predictors that we consider in practice, the slope should become bigger and bigger as I aggregate. In fact, when I aggregate over an horizon h, the slope should become the expression that I have down here. So as you keep on aggregating, the original signal-to-noise type problem should become less of a concern. And that's why we find a lot more predictability over the long run than we find over the short run. Now, one could also show that the R squared from the aggregated regression goes up when you compare it to the most disaggregated R squared. So this very simple structure, which is incidentally the structure that everybody uses out there, says very clearly that, again, low-frequency shocks are just aggregates of high-frequency shocks because we aggregate from a model like that. And again, lack of predictability over the short term and existence of predictability over the long term are effectively the flip sides of the same model. Now I'm going to propose an alternative view. And the alternative view is the following. Well, maybe the low-frequency shocks are not just aggregates of high-frequency shocks. Maybe there are shocks that we want to capture that are not just sums or linear combinations of shocks at higher frequencies. Think about demographic changes. Think about technological changes. Think about political changes. The other idea that I want to capture is that low-frequency economic relations may not imply analogous relations at higher frequencies. Now, the previous model implies consistency between low and high frequencies, right? You may not be able to see predictability over a very short horizon, but it's there. Otherwise, you would not have predictability over longer horizons. So I'm going to propose a framework that effectively relaxes those two assumptions. And the notion of predictability that I will suggest is a notion of predictability that I call scale-specific predictability. But let me get to it. So here is the motivation for looking at a problem in a slightly different way. What I'm going to show you is results that are contained in a paper that I wrote with Benoit Perron in the Journal of Econometrics in 2008. In that paper, what we suggest doing is what we call forward-backward regressions. So what we do is we regress excess market returns aggregated between T and T plus H, where H is a specific horizon, onto variance aggregated between T and T minus H. So, for example, we regress 5-year excess market returns onto 5 years past variance. And we do that in an overlapping type fashion. I'm going to show you a similar exercise. I will use more data than in the original paper. The data is going to be from 1930 to 2013. Forget about the right panels for now. Just focus on the left panels. What you observe there are scatter plots. They're scatter plots of future excess returns on the market onto past market variance. These are scatter plots for different horizons. So in the first plot, up there, we're aggregating over 2 years. In the second plot, we're aggregating over 4 years. In the last plot, we're aggregating over 10 years. What you see is that as you increase the horizon of aggregation, again, returns are aggregated forward, variance is aggregated backwards. As you increase the horizon of aggregation, the relation becomes stronger and stronger. Now, what happens between 4 years and 10 years? So let me show you. So let me show you actual numbers rather than plots. I'm going to come back to the right panels pretty soon. So these are the numbers. What you have in this table are slopes associated with the regression that I just described, future excess market returns onto past market variance. The slopes are for 10 horizons of aggregation, starting at 1 year, ending at 10 years. I'm reporting t statistics, and I'm also reporting r squared. So what you see is that the slope goes up, the t statistics go up, the r squareds go up. If you just focus on the last column, you see that you can predict excess market returns with an r squared of roughly 46% for what the r squares mean. The r squares is about 46%, which means that you can predict excess market returns over 10 years using past market variance with some accuracy. Now, these r squareds are nowhere to be found in the predictability literature. People are usually very satisfied with an r squared of 30%. 50% is rare, very rare. So you could react to this the way I reacted to this when I first saw it and say, this is all spurious. Why? Because we're aggregating, right? We're aggregating forward, we're aggregating backward, we're creating stochastic trends. So returns and variance could be completely independent. By virtue of aggregating them, we're generating unit roots effectively, so they could be independent. They could show up as being correlated in the data, but it could just be a spurious regression problem. Now, in the original paper, we go through a number of exercises to show that that is not the case. But there's one very simple exercise that one can do to show that that's not the case, and it's the following. Let's aggregate forward. If aggregation is what determines stochastic trends, and so if spuriousness is just a result of aggregation, let's aggregate forward, both of them. Well, if you aggregate forward both of them, you find nothing. As you change the horizon of aggregation, the slope becomes flat, remains flat, the t statistics are flat, the r squared is tiny. So there's something fundamental here, and I'm going to show you what I think is fundamental here. But let me continue with this exercise for a little while. So what you have is a representation of the slope as you increase the horizon of aggregation. The top panel is for market variance as the predictor. The bottom panel is for consumption variance as the predictor. So I could do the exact same exercise by running regressions of future excess market returns on past consumption variance rather than on past market variance, and I would obtain the exact same result, which is sort of interesting because the relation between market variance and consumption variance is not that clear in the literature. What you have there is effectively coherent with what you see in the case of the r squareds. The r squareds, as you increase the horizon of forward-backward aggregation, go up all the way to about 50%. So what determines this effect? If we don't believe that it's a spurious result, and I don't believe it is a spurious result, the question is, what gives rise to this effect? Now, what I'm going to try to convince you about is that this cannot be generated by the standard predictability system. So let me go back to the system which I discussed before. So this is the exact same system that we saw earlier. Let me now aggregate forward and backward rather than just forward, which is what I did before. So again, yt plus 1 plus yt plus 2 would give me this expression. I can now collect beta, and I would get xt plus 1. But I don't want xt plus 1. I want xt minus 1 plus xt. Well, I know what is the law of motion of xt, and I can just plug that in. So if I plug that in, what I obtain is this theoretical slope defining the relation between yt plus 1 plus yt plus 2 and xt plus xt minus 1. So again, I'm aggregating forward the regressant, and I'm aggregating backwards the regressor. Now, look at the slope. This slope, since rho is smaller than 1 should go to 0. As you increase the horizon of aggregation, that slope should go to 0. In fact, if you aggregate over h periods, the theoretical slope should be beta times rho raised to the power h minus 1. When h goes off to infinity, that object should go to 0. Now, let me be precise about this. That slope is not the slope of the conditional mean. And the reason why it's not the slope of the conditional mean of yt plus 1 plus yt plus 2 is because there is correlation between xt and epsilon t, for example. So if one wanted to compute the conditional mean of the aggregated y observations, a little bit more work would be required. That conditional mean would still go to 0 with h. So in other words, a typical predictive system cannot capture the increasing slopes that we saw earlier, and of course it cannot capture the increasing R-squares that I showed earlier. So something else would have to be brought into the picture to reconcile the findings in the paper that I discussed earlier. And that's exactly where I'm going. So the increasing pattern in the slopes, in the R-squareds, and of course in the t-statistics, when you aggregate backward and forward, has been found fairly robust in a number of recent studies. You could do all kinds of asymptotics. For example, you could use local to unity asymptotics for the regressor, and you would still find that the result is statistically significant. You could bootstrap the monthly returns, and you would still find that the result is statistically significant. In a 2013 paper, Sidzova assumes that the underlying predictor is a long memory process, and she still finds the exact same result. There is work out there that separates the diffusive component of variance from the jump component of variance, and for the diffusive component of variance, that result appears to be very robust. There are suppressing models out there that deliver that result by using utilities like loss aversion, for example. So the result seems to be in the data, and it seems to have an economic justification. So what delivers that result if it's not the typical predictive system? So here is what I'm going to suggest. I'm going to be thinking about a data generating process, which is a little bit different from the data generating process that I showed you before, which in my view and in the view of my co-author should give us a way to think about that problem. The data generating process will be a linear aggregate of a finite number, j, of scale-specific components. So I'm going to entertain a component model. I'm going to view a time series as a sum of components, as a linear combination of components. The components are going to be autoregressive, but they won't be autoregressive in scale time. The sense of this statement will be clear, the meaning of this statement will be clear in a second. I'm going to be viewing predictability as a property of the components rather than as a property of the raw series. So I'm going to view the return process as being a combination of components. I'm going to view the variance process, for example, as being a sum of components. I'm going to think that a component of the return process and a component of the variance process are tied or linked by a predictability type relation. And that's why I call that type of predictability scale-wise predictability. I'm going to suggest two ways to evaluate scale-wise predictability. One way will be direct extraction of the components. If predictability is a property of the components, let's just extract the components and see if predictability is in the components. The second way will be indirect extraction through two-way aggregation. For that to be meaningful, one would have to show that predictability on the components delivers predictability upon aggregation of the original series. And this is where much of the effort in this line of research was put. We show formally that if you have predictability on the components, that predictability should be revealed when you do two-way aggregation. So the mapping between scale-wise predictability and predictability upon two-way aggregation will be illustrated soon. There's a very large related literature, of course. This all goes back to long horizon predictability, Lafemme and French, Campbell and Schiller, and so on and so forth. There's very interesting work on multi-component type processes in the fractal space. That's the work that was done by Calvé and Fisher in a number of papers. We share some of the intuition of that work, but from a methodological standpoint, we're very different, and the type of problems that we're tackling are very different. In addition, there's an awful lot of emphasis on aggregation in what I'm going to show you that you don't see in the type of work that they do. And then, of course, when you talk about low-frequency dynamics, band spectrum type methods a la Hannon are, a typical tool that people have been using since the 60s. Now, from a methodological standpoint, what we do is fairly close, even though very different, and I'm going to discuss the nature of the difference. It's very close to multi-resolution analysis, which is a technique that engineers use quite a bit. So I'm going to talk about scale-wise autoregressive models. I'm going to define scale-wise predictive systems. I'm going to show you the mapping between predictability on the components and predictability upon two-way aggregation. I'm going to come back to the empirical results and show you in more detail how forward-backward aggregation can be mapped into predictability at the level of individual components of the return process and the variance process. I'm going to show you some simulations, and then if I have time, I'll get to some cross-sectional implications. And in that space, I'll discuss a new notion of risk based on this component-wise decomposition. So here is what I mean by a scale-wise autoregressive model. Take a time series X. Think about this time series as a linear combination of J components. We call these components details. The components are autoregressive, but they are autoregressive in scale time, and the scales are dyadic. Every component captures fluctuations between 2 to the j minus 1 and 2 to the j. So if you think about a situation where you have yearly data, the first component is going to capture fluctuations between 1 and 2 years. The second component will capture fluctuations between 2 and 4 years. The second component will capture fluctuations between 4 and 8. The fourth between 8 and 16, and so on and so forth. So you have a process X, which is an aggregate of scale-wise autoregressive components. What kind of linear combination are we dealing with? The parameters of the linear combination are given by what folks in the multi-resolution literature call the Haar matrix. Now, if I have time, I'll give you some details about the Haar matrix at the end of the talk, but let me give you the intuition behind what we do. In engineering, people usually filter components by using the Haar matrix. The Haar matrix is a matrix with some properties which is used to extract components from an observed time series. We do the exact opposite. Our problem is not a filtering problem. Our problem is a problem which at the end of the day should deliver a data generating process. So we start with the components, and we use the Haar matrix to recover the original time series based on the components. So in other words, we go in the exact opposite direction. The details are autoregressive of order 1 in the dilated time of the scale being considered. This is a choice. One could consider, a more involved data generating process, but for many of the things that we're doing, it turns out that this specification, which is relatively simple, buys us quite a bit. There's 2 parameters involved for every component, of course: rho j, the scale-specific persistence, and sigma j, which is the variability of the scale-specific shocks. Now, since every component is driven by individual shocks, the low-frequency shocks are not aggregates of the high-frequency shocks, which is what you typically have in time series. Both rho j and sigma j can be readily estimated once the details have been extracted, and of course one can use the Haar matrix, the Haar filter, to extract the components. Now, dependency in scale time doesn't have to be very large, and in fact it's usually not very large, but one can show that dependence in calendar time, the components can also be written in calendar time, tends to increase with the scale. I can make statements about the resulting time series under relatively weak condition. The resulting time series is a weakly stationary process. Again, richer specifications for the components could be employed, but the structure that I'm assuming is, at least for these purposes, for my purposes now, rich enough. So here is an example. The black curve is a simulated time series. The blue lines are just extracted components at different scales, going from scale number 1 to scale number 6. And so you see this increasing persistence in calendar time. Now in scale time, you don't have typically the same effect. So again, scale-wise persistence may be a lot lower, and in fact it's generally a lot lower than persistence in calendar time. So I'm going to be thinking about y and x, where y is, for example, excess market returns, and x is a predictor, as a sum of components. And I'm going to define predictive systems on the components. So for example, I'm going to assume that the component j of the return process, yj, is linearly related to the component j of the predictor, xj. So this is analogous to the predictive system that everybody would write, but it's written for the components rather than for the raw series. So it's in effect a scale-by-scale predictive system. So I'm imagining that there is some scale for which this is true, but it doesn't have to be true for all the scales, or if you want, for all the components. So if I have scale-wise predictability, that's the mathematical representation of scale-wise predictability. What's the impact on forward-backward aggregation? And this proposition summarizes the result. So suppose that I have predictability for a very specific scale, scale J star. I dropped the forecast error in the first line, namely up there, forecast error that I had in the previous slide, and I just did it for convenience, but nothing would change if the forecast error were there. So there is predictability at the level of a specific component, J star. What happens if I do backward-forward aggregation on the Ross series? Well, mathematically, one can show that if you do backward-forward aggregation on the Ross series, the largest R squared should be obtained over the horizon 2 to the J star. So the idea is there is predictability at the scale, at the level of scale J star. By doing forward-backward aggregation, one should find the maximum R squared corresponding to an horizon 2 to the power J star. So here is an example. Suppose that there is a component of the return process with cycles between 8 and 16 years that is dependent on a component of the variance process with cycles between 8 and 16 years. The maximum R squared should be obtained when you do backward-forward aggregation for a level of aggregation of exactly 16 years. So this is a pretty clear implication of the model. The model also says that the slope that one would obtain from forward-backward aggregation, namely B, would have to be the exact same as the slope on the components. So, of course, if the model is correct, then we should be finding these results upon two-way aggregation. There are other propositions that one could derive. I'm just going to mention this, but I'm not going to show it to you here. The results are in the paper, but it's just to give you a flavor for the type of implications that scale-wise predictability gives you when you then go to aggregation. You could show that if scale-wise predictability is satisfied for a specific scale J star, when you run forward-backward regressions, but the regressor is in differences rather than in levels. Previously, I had levels. Now, the regressor is in differences. Aggregated, but these are differences. The maximum R squared from forward-backward aggregation should be obtained from a level of aggregation which is now 2 to the power J star minus 1. So if you have a component with cycles between 8 and 16 years of the return process, which correlates with a component with cycles between 8 and 16 years of the variance process, the maximum R squared upon two-way aggregation should be obtained at 8 years when you aggregate forward and backward at 8 years, provided the regression is done on differences rather than on levels. At that horizon, also, the sign of this slope, the slope from forward-backward aggregation, should be the opposite of the sign of the slope which applies to the components. And so one can check in the data if that's true or not. I'm not going to show you anything that has to do with proposition 2, but I'm going to emphasize proposition 1 quite a bit. So if this is all true, that means that one can directly inspect the components to figure out if the components are related and if the relation looks like a predictability type relation, or one can average the data in the way that I described before by doing forward-backward aggregation. I will do both in a second. So let me go back to the data. I am dealing with excess market returns and market variance. The market is proxied by the CRISP value-weighted NYSE Amex index. The data is from 1930 to 2013. These are yearly continuously compounded excess returns. These are yearly variances obtained by summing up squared daily variances. Now, of course, continuously compounded returns and variance aggregate linearly, so finding long-run excess returns and long-run variances is a nice walk in the park. Let me extract components of the return process. These are the first four components of the return process. The red diamonds correspond to the observations in scale time. These are the four components of the variance process. Again, the diamonds correspond to observations in scale time. The multi-resolution literature would call those observations the decimated observations. So let me now go back to the same graph that I had before, but now I'm going to focus on the right panel as well. These are scatter plots on the components rather than on the aggregated series. And so let's focus on this plot. This is a plot that says the component j equals 4 of the return process is very strongly correlated with the component j equals 4 of the variance process. So in other words, graphically, it looks like there is a component of the return process with cycles between 8 and 16 years, which is related to a component of the variance process with cycles between 8 and 16 years. If that's true, proposition number 1 says that we should be finding the maximum predictability upon two-way aggregation for a level of aggregation equal to 16 years. So let's see if that result is in the data. So what I'm showing you now is an extension of what I had in the paper with Benoit Perron in Journal of Econometrics. In that paper, we only had the results on top. Now I'm adding horizons of aggregation. In that paper, we stopped at 10 years. Now we're forward, backward aggregating over, well, all the way to 20 years. The maximum predictability occurs around 16 years. And that's fully consistent, given proposition 1, with having a j equals 4 component of the return process, which is predictable based on a j equals 4 component of the variance process. Look at the R squared. The R squared, in this case, is huge. So what you see in the R squareds is a tent-shaped behavior. They go up like that, all the way to 16 years, and then they go down. That tent-shaped behavior is theoretically implied by the data generating process that I represented before, and it wouldn't be delivered by the classical predictive system. Now, you could argue, how many independent observations do you have over 20 years? Very few. Very few. The point is, I'm not just relying on the 20-year horizon, right? For the theory that I'm presenting, for the data generating process that I'm presenting to work, you have to have a tent-shaped behavior. The tent-shaped behavior requires all frequencies to cooperate, not just the 20-year frequency. So yes, true. I mean, we have very few independent observations at very, very low frequencies. But we're not just relying on very low frequencies. We're also relying on the very high frequencies. The tan-shaped behavior, again, requires all frequencies to cooperate. So what about the details? What you have on top is a predictive relation between components of the return process and components of the variance process for various scales, 1, 2, 3, and 4. And as you can see, scale equal 4 is the scale that gives me the largest R squared. That's the reason why, upon two-way aggregation, I have the maximum R squared for an horizon, which is roughly 16 years. So again, the two results are consistent with each other. What about variance? This is effectively a scale-wise autoregression for variance for every scale, scale 1, 2, 3, and 4. If you look at scale number 4, you see that there's a component of variance with cycles between 8 and 16 years, which is predicted by the same component of variance during the previous 8 to 16 years. Now, of course, this is not very precisely estimated, but we wouldn't expect it to be very precisely estimated, right? So the economic logic of all this seems very clear. This is a pure risk-return trade-off on the scales. There's a very slow-moving component of the variance process, a j equal 4 component of the variance process, which predicts itself into the future. Since variance, slow-moving, predicts itself, that risk has to be compensated. And so we see the exact same effect in the corresponding component of the return process. So at the level of the components, this is from an economic standpoint a pure risk-return trade-off. And then, of course, mathematically, this should translate, if the data generating process is a predictability model in the components, it should translate into maximum predictability upon two-way aggregation over a 16-year horizon, which is exactly what we see in the data. If I were to use consumption variance rather than market variance, nothing would change. Let me just show you plots. As you can see, there is a component of the consumption variance process which is very strongly related with the corresponding component of the return process. If I were to run backward-forward regressions, I would see the exact same pattern that I discussed before in the case of market variance. Namely, I would see R-squareds which increase all the way to 16 years and then decrease almost monotonically. Now, the reason why I find the consistency between market variance and consumption variance interesting is because there's a huge literature that tries to sort of map the two. If you look at the correlation in the raw series between market variance and consumption variance is really, really tiny. And there's a huge literature that discusses that problem. And this is sort of in contradiction with economic logic, right? I mean, you would think that there should be a relation between market variance and consumption variance, but there's none in the data. Now, as it turns out, if you look at the fourth component of the variance process, of the market variance process, and the fourth component of the consumption variance process, those are very, very highly correlated. So here they are. The panel on top has the raw series, yearly. Very little correlation. The panel on the bottom has the two components, j equal 4. The correlation there is effectively 90%. So there is a connection between market variance and consumption variance, but it's not in terms of the raw series, it's at the level of highly persistent, very slow-moving components. This is sort of a story that says, you know, there's an awful lot of fluff in economic time series, right? All we want to get to is, you know, the reliable pieces of it, or pieces of them. And those reliable pieces are usually pieces that move to, you know, with the business cycle, or at frequencies that are even lower than the business cycle. And so it's just a matter of, you know, extracting those components. Okay, so let me show you some simulations. So this is a model in which I'm assuming that there is predictability at scale 6. All other scales are effectively uncorrelated. So what I'm going to do is I am going to work with effectively monthly observations now. So since I'm working with monthly observation, saying that the 6th component is predictable implies that upon two-way aggregation, we should be finding a tent-shaped behavior around 62 months. And so here is the result. I'm running two-way predictive regressions. Around 64 months, I have effectively the maximum R squared. Is it at 60? Is it at 72? Doesn't matter. It goes up like this. Okay. All right, so if I were to do forward-forward aggregation, I wouldn't find anything. So now you may ask, what happens if there is no predictability on the components? What if I do forward-backward aggregation? So would I get the type of spurious result that one would think is a possibility given what the spurious regression literature says? No, actually. If there is no predictability on the details, when you do forward-backward aggregation, you find nothing. Okay. All right, so let me talk about some cross-sectional implications in the remaining 5 minutes. Do I have 5 minutes? You're going to be generous with me? Thank you, thank you. So I'm going to think about a consumption process which can be written as a sum of scale-specific components, of course. The components will represent features of the overall consumption stream with cycles of different length. What I'm interested in is the pricing relevance of individual components. We know that consumption does not price the cross-section of stock returns. This is a well-known result in the literature, and it's a result that has, you know, bothered a lot of people because, of course, consumption should matter. And so the question is, why is it that consumption doesn't matter in the data? So raw consumption doesn't matter, but the question is, are there components of consumption that could matter? So what I'm going to propose is sort of a new risk detection and pricing framework that should in principle identify the components of consumption that do matter. What I will show is that there is a component of consumption that does matter, and that component is what we call business cycle consumption. In other words, there is a component of consumption with cycles between 2 and 8 years, and incidentally, that's effectively the business cycle, that seems to price the cross-section of stock returns very accurately. If I have a little bit of time left, I'm going to talk about the mapping between this and the long horizon betas and show you a couple of additional metrics that could be helpful to evaluate component-wise models. So here is another proposition. This is proposition number 3. Let me assume that consumption growth and the returns on a variety of test assets can be expressed as a sum of components. It turns out that the classical beta of the returns with respect to consumption, in other words, the covariance between consumption growth and the returns divided by the variance of consumption growth, can be written as a linear combination of scale-specific betas, or if you want, component-wise betas. Now, you could react to this in the following way. You could say, well, but that's relatively obvious, right? If the components are uncorrelated, then that's exactly what I should be getting, right? Since consumption growth is a sum of components and the returns are sums of components, the overall beta should be a linear combination of the component-wise betas if the components are uncorrelated. Now, as it turns out, the components are not uncorrelated, they're nearly uncorrelated, but by using the properties of the Haar filter, which is the same filter that I used before, one can show that even though the components are nearly uncorrelated, the actual beta can be written exactly as a linear combination of component-wise betas. So now, if the stochastic discount factor in this economy is a linear combination of consumption components, then I can write a pricing model like this. The expected return on my test assets cross-sectionally should be a sum of risk compensations, where the betas are quantities of risk and the lambdas are prices of risk. So there should be a risk compensation attached to every consumption component, possibly, or maybe not. And so the question is, if this is the pricing model, then one can think of which beta, which component-wise beta really matters. So this is a way to think about which component of consumption is actually driving the cross-section of stock returns. Calculating those component-wise betas is relatively easy, and one can use a component-wise extension of the classical Fama-French framework. So first, I can run time series regressions of the returns on individual assets onto consumption growth for every scale. So this is effectively a component-wise regression of the return on asset I for scale J onto the corresponding scale of the consumption growth process. That's going to give me a component-wise beta. Once I have all of the component-wise betas, then I can run cross-sectional regressions of the average returns on my test assets on the betas to get the prices of risk. And of course, to get the pricing errors as well. So let me show you the data. I'm going to be using 25 standard test assets. These are the Fama-French size and book-to-market sorted portfolio. On this page, we have size. On this page, we have value, book-to-market. So these are effectively 25 portfolios. Size is divided into 5 quantiles. Book-to-market is also divided into 5 quantiles. You see the two classical effects. Average returns tend to go down with size, meaning that bigger firms have lower average returns. but average returns tend to go up with value, meaning that firms with higher book to market tend to have higher average returns. This is typically called the value effect. So for the betas to explain these average returns, they would have to align with these average returns nicely. So let's see whether the scale-specific or component-wise betas align with the average returns that I showed you before. I'm using quarterly data. So scale J equal 2 corresponds to fluctuations between 2 and 4 quarters. As you can see, the corresponding betas tend to capture the size effect, but they don't capture value at all. If I go to J equal 4, 2 to 4 years, the betas tend to turn. So they capture a little bit more value and a little bit less size. As I go to J equal 5, which captures fluctuations between 4 and 8 years, I capture value a lot better and size a lot worse. So as I go to lower scales, you could say higher scales and lower frequencies, I see a rotation of the betas. So I capture size a lot less well as I go to higher scales, but I capture value a lot better. And so I'm going to work with these betas. I'm going to work with the beta associated with the second scale, the beta associated with the fourth scale, and the beta associated with the fifth scale. And the regression that I'm going to run is the second pass regression that I showed you before. So I'm going to regress average returns on the 25 Fama French portfolios onto beta 2, beta 4, and beta 5. What you find is that the prices of risk associated with beta 4 and beta 5 are very highly statistically significant and kind of similar, regardless of whether you have an intercept or not in the model. Even if you have an intercept in the model, and incidentally, the intercept here captures prices mispricing, the intercept turns out to be statistically insignificant. Beta 2 doesn't play much of a role, so let's just can it. Let's just get rid of it. So let me can it. So this is a model in which I get rid of beta 2, and I'm just working with beta 4 and beta 5. The loss in terms of R-squared is not that large. But now, rather than working with beta 4 and beta 5 in an unrestricted fashion, why don't I work with beta 4 and beta 5 by effectively restricting them? If I compute a suitable linear combination of beta 4 and beta 5, I can define a new beta, which is effectively a beta with respect to business cycle consumption. Why? Because beta 4 captures fluctuations between 2 and 4 years. Beta 5 captures fluctuations between 4 and 8 years. And so beta 4 and beta 5 should capture fluctuations over the business cycle. So if I were to work with a beta which captures fluctuations over the business cycle, well, the restriction is not very binding. The loss in terms of R-squared is fairly low. Now, for those of you that have worked in this area, a roughly 40% R-squared with one factor, specifically if that factor is a consumption factor, is fairly unusual. And that's part of the reason why we're sort of excited about this result. We think that there is something fundamental about business cycle consumption as a component of the underlying, of the observable consumption series. So even though raw consumption may not matter because business cycle consumption is swamped by an awful lot of short-term noise, once you extract this persistent component of the consumption process, the persistent component may give you very strong results in terms of pricing. Can I purchase 2 more minutes from you? No, it's too much. It's too much. Should I close? Yeah. Let me. Okay. So let me conclude. We view economic time series as the result of a cascade of shocks. In other words, low-frequency shocks are not necessarily aggregates of high-frequency shocks. The way in which we model this cascade of shocks is by assuming that the time series are effectively linear combinations of scale-specific components. The linear combination is determined by the Haar matrix, but we could have used a different filter. The Haar matrix is just very, very convenient to obtain closed form results of the type of the results that I showed you before when illustrating proposition number 1, proposition number 2, and proposition number 3. Predictability, in our view, is a property of individual components of the return process and the predictor. We used variance, but we could have used any other predictor, and we see very similar results in predictors that people have used routinely in the literature. If that is true, in other words, if predictability is a property of the components, then we have 2 ways to test it. We can extract the components and run predictive regressions on the components, which is something that I did before, or we can do 2-way aggregation. And 2-way aggregation should be consistent with what we see at the level of the individual components. Now, you may say, well, why 2-way aggregation? Why is that relevant? Can I just do predictability on the components? Well, if you think about it, what you really care about is not the components. What you really care about, at least from an asset management standpoint, is the raw series, right? And so 2-way aggregation allows you to make predictability on the components operational in practice because it implies very clear results for low-frequency raw returns. And it's, of course, low-frequency raw returns what you care about if you're doing portfolio allocation, asset management, and so on and so forth. Using this component-wise framework, one can define a new notion of risk. We talked about betas defined on the components. This is useful because the raw series may not be priced, but individual components may be priced. And that's, in our view, exactly what happens with consumption. Raw consumption does not appear to be priced, cross-section, and this is a standard result in the literature. However, there are components of the consumption process that are priced, and we believe that business cycle consumption, a component with cycles between 2 and 8 years, is in fact priced in the cross-section. I looked at the 25 Fama French portfolios. I could have looked at other portfolios, so in some sense I played the classical game and work in the size and book to value space. I could have worked in a broader space, and in fact that's probably something that that I should be doing. But again, I truly believe that there is something in business cycle consumption that we should be paying attention to. Okay, thank you very much.
So I'm going to allow maybe one question, and then we can to stay with the schedule. So we have a microphone, so if people would like to raise their hand first, and I will get the microphone over here.
Thanks. Thanks very much, Federico. I've just come back from Denmark and the Society for Financial Econometrics conference, and we actually had a keynote address by Noor Medahi on the term structure of predictability. And I really wish that I'd heard your talk first, because I might have understood more of Noor's talk if I had. Components of a time series not really a kind of a new thing. Have you thought about components defined in ways other than using a hard decomposition? I mean, if you're asking me, and if Andrew Harvey were here, what he would say is that, all right, well, let's just set the frequency of a cycle to be, t over 2, t over 4, and isolate the cyclical components with these fixed frequencies, and then use these as your kind of components of the series. Do you still find, or have you thought about using these components defined differently to the kind of hard decomposition, explicitly in a kind of a frequency domain? And does this term structure of predictability still hold in your simulations? And the second question, the second part of the question, which is sort of different, we know that in these returns we have errors which have very thick tails. Does the structure of the errors in the excess returns, you've used white noise mainly, does that have any kind of distorting effect on the term structure of predictability?
Yeah. So we've played around with all kinds of different models for returns, and the results haven't changed at all. Meaning that once you extract the components are going to have their own dynamics. And then it's an empirical result as to whether you have components of the return process and components of the predictor that are correlated or not. So in other words, let me back up a little bit and rephrase. One question that you're asking has to do with filtering. The other one has to do more with the DGP. The second one has to do with filtering. I'm agnostic about the properties of the return process and the predictor. So in other words, if I can apply a hard filter or any other filter for that matter and extract components, then it's just a matter for me from an empirical standpoint to evaluate whether the components are related somehow by a predictive type regression. So in other words, I don't have to make strong assumptions on the properties of the return process or the predictor to be able to apply these filters and extract the components. So that's from a filtering standpoint. The other question had to do with how do I think about the components. Now, it is true that I could entertain a variety of component-wise models. But it is also true that what I have in mind is a data generating process, right? So what you're referring to is effectively a way to estimate these regressions, right? I mean, so could I do band spectrum type analysis to evaluate at which frequency I have some sort of predictability? I could, and those regressions would give me effectively the same outcome that my forward-backward regressions would give me. But if I were to obtain the same outcome, I would still not know what the underlying data generating process is. What I'm thinking about here is not inference. In other words, I could do inference to evaluate predictability at low frequencies in a variety of different ways, right? I mean, I could do it doing, forward-backward aggregation. I could do it using, band spectrum regression, provided it's done accurately, right? I mean, it has to be predictive, right? Yeah. So it has to be adapted to time t information and so on and so forth. But I could do that. So I could do everything in frequency domain. Sure, of course. This is still not answering the question, what is the underlying DGP, right? And so that's where we think the contribution of this line of work is. I mean, we have to think about a DGP that would deliver either predictability upon two-way aggregation or predictability if I were to, run spectrum type regressions. And so you can view the Haar filter as a filter. The way we're using the Haar filter is not just as a filter, it's also as a way to define the DGP, right? I give you the components, I give you the dynamics of the components, and then once I have the components with their dynamics, I use the Haar filter to obtain the final, the final series. I could use a different structure, right? I mean, I could use, Debussy type filters or other filters as well. So for me, it's not a filtering problem, even though I need to filter to get to the components. For me, it's more of a of a DGP type problem, right? I mean, so what's the underlying data generating process? And the underlying data generating process uses the filter just as a way to find the raw series given the components. Did I answer? Yeah.
So I'm going to, because people are trying to get to the next section, so Stephen, you can. So just for the last of my duties is to say many thanks. And,
my goodness, thank you so much. Thank you very much.
Thank you for your lecture. We shall talk more outside.
Absolutely.
So thank you very much.